Hey, my name is Julian, and I will present to you HyenaPixel Global Image Context with Convolutions. This is a joint work with Professor Sebastian Huben and Professor Sven Behnke. What is global context? So for convolutions, we typically have local operations with kernels of the size 7 by 7, 3 by 3, where only a fraction of the feature map is covered and can influence the output value. So we require a stack of those layers to actually capture global context. For attention, this is a different story here. All input tokens can influence the value of the output token, and we have global context natively. The property of global context is often linked to better performance for vision applications, but replicating this property has challenges. For example, the computational complexity increases with the number of tokens that you consider, and you have to deal with training instabilities. There are a few works that try to achieve global contexts with convolutions like the Global Convolution Network and SecNext that both apply separate convolutions up to the size 21 by 21. We have RepLKNet that has regular convolutions with the size 31 by 31. And we have SLAK that uses two parallel kernels with dynamic sparsity and has filters up to 61 by 61. However, not even the last method, SLAK, fulfills the property of global context. So here we maybe have at the center evaluation position, we have global context, but once we move this large kernel to the borders or corners of the feature map, some part of the feature map will be not covered by the filter. Another solution can be Hyena, proposed by Poli et al. This was meant or was proposed as a substitute for attention for causal language modeling or next token prediction. And it uses a Fourier transform to accelerate its internal global convolutions and thus achieves subquadratic complexity in the number of tokens. So how does it work? So we start with the first element in the recursion. So y0, here we element-wise multiply the two projections of the input sequence x. And we use that in the recursion on the right side. So here we first apply the function g to the previous output and element-wise multiply that with the next projection. And we can repeat that multiple times. Function g is a global convolution with an implicit filter. And this implicit filter is the same size as the input sequence x. It is created by first defining the position encoding, applying a feed-forward network to that encoding, and finally multiplying everything with element-wise multiplying everything with the window function. Here in the window function, the first or the most recent element in the sequence gets the highest value, and then we have an exponential drop-off into the past of the sequence. We can write this explicitly for def of 3. So here we apply the function g 3 times, and we have 5 projections in total. For our case, we can simplify that even more by only having one recursion and applying the function g 1 time. And we can also rename the projections to query key and value as we are used to from attention. If we visualize that, we see directly a problem. So here the first token in the input sequence can only be influenced by itself. And this is maybe a good property for natural language processing, but it's not really great for vision applications. Therefore, we propose bidirectional Hyena by extending the filter into the other direction, and we update the window function to have an exponential decay to both sides and the highest value in the center. Another natural extension is HyenaPixel. So here we not only have bidirectional modeling, but also keep the 2D structure of images intact. Let's look at the architecture of the HyenaPixel operator. So we first have our input projections as usual. We split the output of that along the channel dimension into query key and values. We element-wise multiply query and keys, and we apply a normalization. This normalization is extremely important for training stability. We create our filter by starting with a position encoding a feed-forward network, and we apply that the result of that with the window function that also has the highest value at the center and an exponential drop-off to the corners. The filter is then convolved with the feature map or the output of the query key element-wise multiplication. Note that the filter is almost twice the size of the feature map to ensure full coverage at each evaluation position. The output is element-wise multiplied with the values, and we are done. We integrate our operators into the metaformer. So the metaformer is a hierarchical architecture that is tested with multiple token mixers. So we have a nice ground for comparison. So for example, the conformer that has convolution in each stage, or local convolution, and the CA former that has local convolution in the first two stages and attention in the last two stages. We trained our models on ImageNet 1K, and I will not bore you with numbers, but just get directly to the key takeaways. So first of all, bidirectional Hyena performs better than current ConvNets and scales pretty well in a number of parameters. If we combine HyenaPixel with an additional attention layers in the last two stages, the performance actually improves, so it can benefit from that. However, if we do the same for bidirectional Hyena, so the 1D variant, the performance actually decreases. We assume that the features learned by bidirectional Hyena are simply not compatible with attention. In our experiments, we observed that between two networks or trained networks, about 50% of the wrongly classified images differ. So we decided to simply combine two models by meme pooling the logits, and as you can see, we can simply achieve competitive performance without training. In our ablation, we first tested the kernel sizes of HyenaPixel, and we saw that we have some robustness here, so the model is not really affected by changing the kernels. We assume that it finds a pathway to capture global context over the hierarchical structure. Bidirectional Hyena performs the best among our token mixers we have here. Interestingly, regular hyena, so with the causal language modeling objective, and HyenaPixel with separate convolutions have the same performance. So this operation is similarly restrictive. Layer normalization not only stabilizes our training, as already mentioned, but also improves the performance slightly. And finally, we tested how effectively HyenaPixel can capture global context. We limit the network depth to 4, so we have only one layer per stage. And as you can see, if Conform and HyenaPixel are trained on a regular resolution of 224 by 224, they perform similarly. But if we increase the resolution to 512 times 512, the gap increases, and HyenaPixel performs significantly better and thus more effectively captures the context of the image. We also visualize the effective receptive field. So the effective receptive field is basically visualizes the influence of all input pixels to the centermost output position. This is done by tracking the gradients and the backwards pass by passing multiple images from ImageNet through the network. We see that most operations are more local. SLAK has a larger effective receptive field, but some off-center features. If we look at the HyenaPixel, we see that it covers the whole effective receptive field visualization. It has some horizontal and vertical artifacts, but these disappear once we use convolution in the first two stages of the network. We provide further information in the paper on object detection, instance segmentation, and semantic segmentation. We also look at the learned filter sizes and truncate them to see the impact on the performance, and we also visualize them. In summary, bidirectional Hyena and HyenaPixel almost close the gap between ConvNets and attention-based networks for vision applications, but there's still some room for improvement. We achieve global context with convolutions and perform on par or better than other ConvNets. By using a fixed pixel neighborhood, such as HyenaPixel does, you actually trade accuracy for other properties such as dynamic input size, which could be favorable for example, for object detection. Further directions could focus on improving semantic segmentation results. So this is one task our model underperformed in. For example, you could add a residual connection with a local convolution to capture texture-based features. You could use our insights to optimize model layouts. By selecting the ideal filter size, for example, or you could apply our models to applications that require efficient processing or that are higher dimensional, such as video data. And with that, I'm at the end of my talk. Thank you for your attention.